Welcome back, everyone. Last section, last push for this. We're going to do some calculations, and hopefully, because I think there are probably some questions still about the direction in change in momentum, hopefully that'll get sorted out as we go along. Okay, so let's just hop in there. So what we have is this. A soccer ball with a mass of 425 grams, that's the average mass of a soccer ball, is moving at 2 meters per second to the right. A soccer player kicks the ball so that its velocity is now 3 meters per second to the right. They ask you to calculate the ball's change in momentum. So, what I suggest, draw a diagram, okay? This isn't a particularly difficult situation to understand, but we all think better when we can visualize it, okay? Now we know I can't draw, so we're just going to go with it. So what we have is we have the foot of the soccer player. Here's my ball, okay? The ball has a mass of 425 grams. It's initially moving at 2 meters per second. Then the soccer player kicks the ball. There we go. So here's his leg again, which has changed size and shape, but we're not going to worry about that. And now the soccer ball is still going to the right, and it's going at 3 meters per second. They want the change in momentum. They're not looking for force, they're not looking for any of those, they want change in momentum. So we know change in momentum would be final minus initial. You absolutely can do this question so that you first work out the final momentum, you work out the initial momentum, and then you minus the two. You're more than welcome to. But remember, we can do this equation, which you've seen, to look like this, where we take mass and we take final velocity minus initial velocity. That's the way I'm going to do it. The reason why I do it this way is I'm doing less equations. I'm less likely to make a mistake that gets carried down, okay? Because it's easy to make mistakes. We all do them. So we want to try and avoid it, okay? And I wouldn't say this with every section, but with this one in particular, trying to keep it all in one equation is a good idea. Now, the mass of my object is 425 grams. Remember, we can't work in grams. So we have to change that to kilograms, which means we're going to divide by 1,000. Just quickly, your information sheet always says round off your final answers to at least two decimal places. That doesn't include conversions, okay? So I can't convert this and now round this off to 0.43. Because it's not 430 grams. When I convert this, I have to keep all the decimals. All right, that is not an option here. Please be careful, because if you change it to 0.43 kilograms, they're going to mark your substitution wrong, which means you don't get the final answer right either. So be careful. Let's substitute in what I know, okay? So I've got 0.425. Final velocity was 3. Initial velocity was 2. Okay, I'm going to do it on my calculator because it's important that we know. So what have we got? Okay, we've got 0.425 times, there's my bracket, 3 minus 2. Not allowed to have a fraction, must convert it. Oh, look, 0.425. So, we get a positive answer of 0.425 kilogram meters per second. Now, what I haven't done is said what a positive answer means, because we just went ahead and did it. What we have done by default, without even thinking about it, is we've made to the right our positive direction, because none of these are negative. We've left them as positive. Be careful here, because this was done by default. You need to think about what that how that happened, okay? We have to always allocate a direction as positive when we do calculations like this with vectors. I would have, if I'd actually thought about it at the beginning, gone to the right as positive. My default, in other words, what I do naturally when I look at calculations that require a direction, is I make original direction of motion positive. That doesn't mean that I'll always get a positive answer at the end, or I'll always get a negative answer at the end. It just means that every time I look at a question, I'm starting from the same point. So it's one less thing for me to think about before I get going, because it's just a natural. Original direction positive, which means here original direction is positive. I got a positive answer at the end, which means that is to the right. Okay? Straightforward. Now for the fun part. Draw a vector diagram representing the change in momentum. What we're actually going to do is I want to show the initial momentum, I'm going to show the final momentum, and then I'm going to show you where the change was, okay? We didn't work out the values of the initial and the final momentum. We don't need it, okay? Final velocity was bigger than initial velocity, which means final momentum is going to be bigger. I'm just going to draw it as a bigger line. Okay, so initial momentum is going to the right. Final momentum is going to the right. Now, change in momentum always goes from the end of the initial to the end of the final. There's my change in momentum. And it's tiny because we knew that that was 0.425. It's tiny, okay? So we've got the initial and the final, and then we've got the change. So remember, the initial and final momentums must start at the same place. Little different to what we're used to when it comes to vector diagrams. Okay. Now, same soccer ball. Moving at 2 meters per second to the right. Now the goalkeeper catches it, and the ball stops. Final velocity is 0. Then they ask, what is the ball's change in momentum? We have to have a direction as positive, which is going to be to the right. Now we've got to say to ourselves, are we expecting a bigger change in momentum than before, or a smaller change in momentum? And here, the more you do this, the more you'll realize how this is going to work. In the first question, it went from 2 meters per second to 3 meters per second. Its velocity only changed by 1. Now it's going from 2 meters per second to 0. The velocity is changing by 2. That implies for me that the change in momentum must be bigger. That's what my head is telling me, okay? Let's see if that's the case. So, we could draw a diagram, but I think this one's easy to understand. So we're going to do change in momentum. This time I'm going to start by saying that it's m delta v. It's one of the equations. We know we can use it as it is. Okay, again, if you want to go calculate the final momentum, calculate the initial momentum, minus them from each other, you're welcome to do that. Okay, so my mass, because we worked it out last time, 0.425. Final velocity is 0. Initial velocity is 2. I'm hoping some of you are looking at this and going, hang on, wait. We're going to get a negative answer. Yes, we are. Now I want you to think about whether that makes sense. We'll talk about it. So, in other words, my calculation, 0.425 is 0 minus 2. Okay, we can't use a fraction, so we get negative 0.85. Number one, it's bigger than the last one we did. We expected that. Number two, it's negative. That means that the change in momentum is to the left, because our answer is negative and the positive direction is to the right. So this becomes 0.85 kilograms meters per second to the left. Now, we've done Newton's second law in terms of momentum. We also said that the net force would be in the same direction as the change in momentum. That means the net force that's acting on my ball must be to the left, which makes sense. The ball is going to the right. The goalkeeper catches the ball. So the goalkeeper must be exerting a force to the left to get it to stop. If the goalkeeper is pushing the ball to the right, I was going to get there eventually, the ball's not going to stop. It's going to go in the goal, and then no one's going to be happy, okay? So the goalkeeper has to be in the opposite direction to the motion of the ball so that it will stop, okay? We expected a bigger change in momentum because there was a bigger change in the velocity. That one was fairly straightforward to get. If we now look at the diagrams, all right, I'm going to do all three again. Initial momentum, okay. Final momentum, nothing. Okay, didn't go anywhere. I can't draw a diagram, it's 0. Now, change in momentum has to go from the start of the first one, oopsie, to the end of the first one to the end of the last one. It goes backwards. And in fact, the change in momentum would have been the same as the initial momentum. It's just in the opposite direction. So it goes backwards. The thing here is where it starts. That's the big thing. Okay? That one's not so bad. But what if the ball changes direction? So we've done same direction speeding up. We've done same direction slowing down, essentially, or stopping. Now what happens if the ball changes direction? So, same ball. Same initial velocity, so I'm still going to take to the right as positive. But now a soccer player comes along, because he's trying to get a goal. Now we're not going to let it go to the goalie. And he kicks the ball so that its velocity is now 3 meters per second to the left. The ball has changed direction. Now we've got to think about it and go, well, are we going to get a big change in momentum or a small change in momentum? I'm actually not going to tell you. Okay, I want you to look at the value. So we've got a 2 and a 3, but there's a change in direction. So actually we've gone from plus 2 meters per second to minus 3. Think about that in terms of a number line, because we're actually looking at how many spaces on the number line there would be. So we've got to go, yeah, I'm going to let you think about that. Let's see what we get to at the end. So we want change in momentum. Change in momentum is m delta v. The mass hasn't changed. It's been wonderful. So it's 0.425. Final velocity was minus. So it's minus 3, minus 2. Hopefully, some of you are going, hang on, wait. We're going to get a negative change in momentum. Is that going to make sense? Well, let's see. Okay, so calculator, 0,425 minus 3 minus 2, close our back brackets, fraction again, minus 2,125. So that means that my change in momentum is to the left. Let's think about that. The ball came along, soccer player kicks the ball so it changes direction. The change in momentum must be in the opposite direction. The net force on the ball must be in the opposite direction or the ball's not going to change direction. So I'm okay with that. But it's a big change in momentum. It's the biggest one we've done so far. Why? Because of the change in direction. So this makes this 2,125 kilogram meters per second left. Okay? Guess what we're going to do? Because we've done it lots today. We're going to draw the diagrams. So, initial momentum. Now watch what happens. My final momentum is in the opposite direction, but remember, we start from the same place. Now my change in momentum goes from the end of the first one to, there we go, I'll draw it all nice for you, to the end of the last one. There's my change in momentum. And it's a much longer line. Okay? Change in momentum is related to the net force. So in your head, when you do these calculations and you get to the final answer, you've got to say to yourself, does it make sense with the direction? How did the force applied interact with the object to get the change? Then it'll make sense to us. Then we can picture it. Then we can go, okay, that makes sense. I can work with that. Okay? So, what does the size of the change in momentum tell you? Well, it tells you about the net force. It tells you whether it's a big change in momentum or a small change in momentum. It can also tell you whether it changed direction. Okay? So the size does mean something for us. When there is a change in direction, there's always a big change in momentum, okay? So there we go. What I'm trying to get to with this is you saw, so with the first equation, it went from 2 meters per second to 3 meters per second, but it was in the same direction. So it was a small change in momentum, and it was a positive change in momentum. When it went from 2 meters per second to -3 meters per second, velocity magnitudes are the same, but because we changed direction, big change in momentum, okay? That also means that for it to change direction, we needed to apply a bigger force. Net force is directly proportional to the change in momentum. So if I want a big change in momentum, I have to apply a big force. If I want a small change in momentum, and I have to apply a small force. But what I need you to remember here, and this is important, when there's a change in momentum, we always get a maximum change in momentum when there is a change in direction. Okay, so when you look at a problem and you see that it's something like a ball being hit by a tennis racket, okay, it's going to change direction. The hockey stick that we've done before changes direction. Cars are a little different because, of course, we could be going forward and slow down, forward and speed up, but it's still part of that, okay? So that whole change in momentum is related to F net. Same direction. When we get onto collisions, which we're going to do in the next lesson, that becomes quite important, okay? And when we get to impulse near the end, that F net being in the same direction as change in momentum, vitally important for us to get. Okay, very, very, very important. So, what have we done? When the velocity of an object changes, the momentum of the object changes. Change in momentum and net force are in the same direction. No, I'm making a big deal out of it because it's important. Change in momentum can also be represented by a vector diagram. And that one you maybe have to go through again. So, that's the end for today. So we've done a lot, okay, which you need to keep in your mind. Next time, we're going to look at collisions and explosions. Very exciting, okay? But until then, think about what we've gone through. Go and revise it. I promise you, you can get this. But I'll see you next time.